Hello students, and welcome to section 7-6, rational exponents. So rational exponents and radicals, as you can see, the definition to begin of b raised to the 1 over n power states that for any real number b and any positive integer n, b raised to the 1 over n is equal to the nth root of b, except when b is less than 0 and n is even. And then the definition of b raised to the m over n states that for any non-zero real number b and any integers m and n with n greater than 1, b raised to the m over n is equal to the nth root of b to the m, but also the nth root of b, the whole quantity raised to the m power, except when b is less than 0 again and n is even. This particular version of this particular definition is probably the most useful in pretty much every single problem that we're going to be doing in this section. So for example, it says write 28 to the 1/2 in radical form. It says first notice that 28 is greater than 0, so that when we do this we'll be rewriting it as such. The square root, again the 2 in the denominator is the index we call it. So the square root of 28, the radicand raised then to the first power, the numerator of the exponent. It is wise to put the 1 outside of the root, although you could also put it inside of the root. These two versions are essentially acceptable when we rewrite this version of the exponential form, the rational exponent in particular of m over n. However, this version is probably most preferred, as we're going to see in many problems. It turns out 28 can be rewritten using the product property as you see 4 times 7. You can also use, of course, a factor tree. 4, of course, ends up being a perfect square, so 2 squared and then times 7. Individually, each root can be rewritten as such, so the square root of 2 squared, or the square root of 4, which we know to be 2, and then the square root of 7 as you see as is. Can't do anything more to that. So the final answer is simply 2 root 7. Example 2. Turns out the original problem, it says evaluate -8 over -125 to the 3rd power. Because we're dividing two negatives in the end, the entire base here ends up being positive. Now, I ended up just simplifying it originally as such, although as you can see here they denoted that -8 and -125 because they're less than 0 each, and of course because your index, which ends up being 3 because of the denominator of your exponent, 3 indicates of course a cube root, but of course also because it's odd we are able to individually cube root the numerator, and separately there you could see the denominator. In the numerator, the cube root of -8, you can end up rewriting as follows, as you can also with this denominator, the cube root of -125 as follows. Now I simplified it a little bit more specifically, again from up above, changing each sign to a positive, because a negative divided by negative of course is a positive. So now we have the cube root of 8 over 125, and yes, you can split it back up again. I'm just showing you two different versions here, one with both negatives and one with both positives. In the end, you can in fact combine the fraction, or you can split up the fraction with two separate radicals. And then you can go ahead and take the cube root of 8, which we know to be 2, the cube root of 125, which ends up being 5, right? 5 to the 3rd power is 125, and 2 to the 3rd power is 8. By virtue of their approach using this particular sign and that particular sign, you get -2 over -5, which of course ends up being the same thing. So I have several exercises to kind of run through, or at least we can highlight maybe some key ones and ask maybe that you take a look at others later. As we go ahead and take a look, it just simply says write each expression in radical form, or write each in exponential form, starting from radical form. So simply number 1, 11 to the 1/7 power can be rewritten with an index of 7. And then we're going to be doing what? The root of 11 to the 1st power. On this particular problem, I opted to put the 1 under the radical along with 11. However, you could very easily just as well write it outside of the root, which I actually recommend. And if you note number 3, 300 to the 3/2 power. Again, this is the exponential. Rewriting it as a radical, we've got a square root, so there you have it, of 300, the entire quantity cubed. This is more advantageous when it then comes to simplifying later. You can see numbers 2 and 4 are very much similar, except on number 4, you're rewriting from radical form to exponential. So it's a square root, therefore the denominator of the exponent is 2. 47, of course, is your base because that's the radicand, and again, because it's to the first power underneath the root, it becomes the numerator of your exponential form. Number 5. This is a cube root of this whole quantity, so individually 3 can be raised to the third. A to the 5th can be cube rooted, of course, such that it's now 5/3. And the same goes really with b squared, where b to the 2/3 is our exponent. On number 6, you see that same basic shape, so to speak, such that 162 is raised to the 1/4. Again, the 4th root tells us this, and then p to the 5th. In other words, the 4th root of that is in fact just simplified as follows: p to the 5/4 power. 7 through 9, all of these are very neat segue questions, so to speak, such that if you start with something of this nature, -27 to the 2/3, I'll ask that you maybe try this without a calculator, and I'll ask that you also look at my steps, of course, to see that it makes sense. So the cube root of, because there's the denominator again, 3, now the index, the cube root of the base -27, the entire quantity. I didn't use parentheses here, but I think it's obvious enough that the 2 is the exponent outside of the root. Individually, if you just work with the cube root first, of course, the cube root of -27, because this is odd, and because, of course, this is a negative, it's -3. And again, think of -3 to the 3rd power. Yes, it's -27. That 2 outside the radical stays as is. So now the next step, of course, once you square -3, you end up with 9. Now think about this. If you happen to put the 2 under the root, you'd have a rather large quantity to take into account. It'd be -27 squared. Okay, and that's not necessarily as easy to work with as -3 quantity squared, I would argue. So it's much more advantageous, hopefully you could argue, for you putting the 2 outside the root. Number 8, 216 to the 1/3. In other words, the denominator there becomes the index, so the cube root of 216 to the 1st power. 216 does in fact end up being a perfect cube. And then the factor tree approach, you see 3 6s, and there you have it. Those end up being cube rooted to give us 6. 6 to the 3rd power again. Because it's 216, we have the cube root of which ending up being 6. Number 9, 0.0004 to the 1/2, or 4 over what? Tenths, hundredths, thousandths, 10,000ths. So 4 10,000ths as a fraction, square rooted, again, because again the denominator dictates the index. Exponent of 1 inside the root or outside, it's actually negligible here. The square root of 4, of course, is 2. The square root of 10,000 is 100. This does, in fact, nicely reduce to 1/50th and 0.02, as you see. If you use a calculator on any of these questions, that's acceptable, but I still ask that you try, at the beginning at least, try to see if you can do a good majority of it without a calculator. All right, moving forward here. So if you take a look, simplifying expressions, and we'll go ahead and obviously jump in with the examples in a moment here. We have first all the properties of powers from lesson 6.1 apply to rational exponents. When you simplify expressions with rational exponents, leave the exponent in rational form and write the expression with all positive exponents. Any exponents in the denominator must be positive integers. When you simplify radical expressions, you may use rational exponents to simplify, but your answer should be in radical form. Use the smallest index possible. So for example 1 says simplify. You see y to the 2/3 times y to the 3/8. Keep in mind, because our bases are the same, you are allowed then to add the exponents. Now 2/3 and 3/8 added are not particularly nice because you don't have a common denominator. However, if you think of 3 and 8 leading to an LCD of 24, this simply multiplies to 8/8 to get that denominator of 24, and this, as you see, multiplied by 3/3 to get again 24. So you've got 16 24ths plus 9 24ths, as you can see here, which lends itself to your final exponential form of y to the 25 24ths. This is a perfectly good final answer for that type of problem. Example 2. Simplify the fourth root of 144x to the sixth. First and foremost, you can rewrite it, and probably should at least consider rewriting it, where 144 times x to the sixth is raised then to the 1/4 power. So the rational exponential form now translates by simple simplification of 144 to the fourth, separately then times x to the 6/4, because you're just multiplying 6 times a fourth. Okay, fair enough. 144 you can rewrite as 2 to the fourth times 3 squared. Think about the factors, right? Turns out that 2 to the fourth and x to the sixth, partly at least, are in fact perfect fourths. But 2 to the fourth is more obvious, such that if you raise 2 to the fourth, or 4 times a fourth, of course, you get 2. Because again, 2 to the fourth is a perfect fourth. 3 squared is not a perfect fourth, but if you go ahead and multiply 2 times a fourth, in the next step, 2 times a fourth, of course, is a half, so you have 3 to the half. Interesting. So the problem ends up being, at least in that particular term, not a fourth root, but a square root, which you'll see here in a moment. Similarly, x to the sixth to the fourth, because again, we can multiply here as such, where you get 6/4. 6/4 is reducible, reduces to 3/2. Okay, and as it turns out, an additional step that you can take into account, and probably should, of course, wherein you're asking to take the square root of something raised to the third power, right? X to the 3/2 is the same as the square root of x cubed. And if you think about x cubed as x times itself 3 times, and of course x times x, or x squared, is something you can square root, you'll end up with x outside the root. You'll be left then with x inside the root. Remember, the 2 from earlier is outside because 2 to the fourth was a perfect fourth, and the 3 isn't a perfect square technically, and the final answer then ends up being 2x times the square root of 3x. It is also acceptable to rewrite it as such. I would rather you get more comfortable with roots in general, because they're easy to work with and manipulate later. Okay, some more problems to take a look at. And no, I'm not going to finish all of these. There's a good number here for us to dig into, maybe during actual class time. Number 1, just to take a look, you've got x to the 4/5 times x to the 6/5, because again, x's are the same, the bases particularly are the same. You can add 4/5 and 6/5, which of course is 10/5, and then in turn simplifies as 2, so x to the 2nd. Number 2 is very interesting because you can multiply the exponents, and because these 3's nicely cancel, you'll be left with 2/4. Because 2/4 is reducible, you'll have y to the half, and of course in that regard you can simplify or rewrite as such, the square root of y. I'd like you to direct your attention actually to a couple of division problems, particularly number 7. Okay, look at the exponent. It actually is 1 to start with, but because the bases are the same, because you're allowed then to subtract exponents, you should consider the idea of common denominators, right? So getting a common denominator of 3, here of course 3/3, and here 1/3, subtracting 3/3 minus 1/3 ends up being 2/3. Please also take a look how number 8 unfolds. This turns into 3/6. This turns into 2/6, knowing again we got to get a common denominator, and then subtract 3/6 minus 2/6 to get 1/6. If we take a look at number 9, this is not a perfect sixth. Turns out though, when you make your factor tree, you can see 64, which ends up having obviously 6 factors of 2. You're left with 2 times the 6th root of 2. Please look ahead in advance of our homework, taking a look then at number 10 and 13 to get better perspective on how to do all of these problems. And you'll see that it unfolds quite nicely.